Hey, hello everyone. Welcome to today's Leetcode discussion stream of Biweekly Contest 174. We will be discussing all the problems today. So let's start with the first problem, which is best reachable tower. The problem says that you are given a 2D integer array towers where tower I is a vector which is represented by three parameters xi, yi, and qi, and xi comma yi represents the coordinates and qi represents the quality factor of ith tower. You are also given an integer array center representing your location and an integer radius. A tower is reachable if its Manhattan distance from center is less than or equal to radius. What is Manhattan distance? Manhattan distance is just the absolute sum of absolute values of difference of coordinates. All right. Among all reachable towers, return the coordinates of tower with maximum quality factor. If there is a tie, return the tower with with the lexicographically smallest coordinate. If no tower is reachable, return -1, -1. So what does the problem say? The problem say that we are given a center point. Let's say we are on a 2D coordinate plane. For example, the laptop in front of you. Let's assume that the center of your laptop is the origin. Now the center is given at 1 comma 1 on the coordinate plane. Now there are some towers present at 1 comma 2, 2 comma 1, and 3 comma 1. The tower at 1 comma 2 has quality factor 5. Similarly, tower at 2 comma 1 has quality factor 7, and tower at 3 comma 1 has quality factor 9. Now we are given a radius 2. Now all the towers which have their Manhattan distance from center smaller than equal to 2, they are called reachable towers. Alright. Now, among all such towers, we want the tower with maximum quality factor. If there are multiple towers with maximum quality factor, let's say there were 2 9 here, then and both were reachable, then there is a case where we have two towers which have maximum quality factor and both are reachable. So among them, we need to return the tower that is lexicographically smallest according to the coordinates. All right. What do lexicographically smallest mean? It means that first we compare the x coordinate of both the points. If one has a smaller x coordinate, then that is lexicographically smaller. If the both of them are equal, then compare the y coordinate. Then if one of them has smaller y coordinate, then that is lexicographically smaller. All right. So let's try to solve the first test case. So the first test case is 1 comma 2 with quality factor 5, 2 comma 1 with quality factor 7, 3 comma 1 with quality factor 9. Let's compare the distance of all these towers from center. The first tower represented by T1 has distance is equal to 1 minus 1 which is equal to 0 and 2 minus 1 which is equal to 1. Alright. So it is reachable because it is smaller than equal to radius. Now the second tower. It has coordinates 2 comma 1 and center is 1 comma 1. So what is the difference of x coordinate? It is 1. What is the difference of y coordinate? It is 0. So distance is 1 and it is reachable. Similarly, the third tower, x coordinate is 3 and 1, difference is 2, y coordinate is 1 and 1, difference is 0. So total distance is 2 and it is smaller than equal to radius. So it is reachable. Alright. Now among these three, which among them have highest quality factor? Obviously, it is the one with quality factor 9, that is tower 3. So we need to return its coordinates, which is 3 comma 1. That is the answer. Now let's move to the second and third test cases. We again have three towers. Tower 1, what is its distance from center? Uh, it is equal to 4. What is the radius? 5. So it is reachable. Similarly, tower 2, what is its coordinates? 2, comma 2. What is the distance? 2 plus 2. It is equal to 4. It is reachable. What is tower 3? It is 4, comma 4. What is the distance from center? It is equal to 8. It is not reachable. Alright. Among the reachable ones, which one of them has highest quality factor? Both of them have same quality factor. So what do we need to do? We need to return the one with minimum lexicographically coordinates. Minimum lexicographical coordinates. Okay. Among 2 comma 2 and 1 comma 3, which has the smaller x coordinate. Obviously it is 1 comma 3. So we need to return 1 comma 3. Alright. Now let's move to the third test case. It is 5 comma 6. Center is 1 comma 2. So distance is 4 plus 4, which is equal to 8. Is it reachable? Radius is 1. So it is not reachable. Now tower 2. It is 0 comma 3 with 1 comma 2. Distance is 1 plus 1, which is equal to 2. So it is not reachable. Alright. Now the third test case or third tower. Okay, there is no third tower. So both of them are not reachable. So the answer will be -1 because we cannot reach any possible towers. So we return -1 comma -1. Alright. So what is our observation and implementation? We can iterate over all the towers, check if it is reachable or not reachable. Just what we are doing manually. Okay, we can just compute it with a for loop. Now, among all the reachable ones, if we find that the current reachable tower has quality factor more than uh, the last previous reachable tower, then we say that this is the required tower and increment the maximum quality factor we have inculcated so far as the current quality factor. Now, if the quality factor is equal to the current quality factor, that is the current quality factor, which is equal to 4 here. It is equal to the previous max, which is equal to the 4 we have inculcated previously. Alright. If this is the case, then we compare the x coordinate and y coordinate we have stored till far so far because initially when we were computing the answer at index at tower 2, we had stored the coordinates of tower 1, which is equal to 1 comma 3, and now when we see that previously inculcated max, which was 4, is equal to current quality factor, which is equal to 4, then we compare the current coordinates with the past coordinates. All right. So after comparing, if the current coordinate is smaller, we update the coordinates as current coordinate. All right. So let's see how to implement this. Initially, let's say the tower we have reached till okay, the previously inculcated towers are null. So we want that lexicographically we always win. All right. So how can we win lexicographically? Always. If we have very high values. Okay. So just insert int underscore max in both x coordinate and y coordinate. All right. Now max quality factor inculcated so far. We want it to be minimum possible. Okay, so that the very first quality factor which we inculcate is uh, equal to the current max. So let's assign it as int min. Now iterate over all the towers, store the x coordinate, y coordinate, and the current quality factor. Calculate the distance from center. Now, if it is less than equal to radius, then it is reachable. Now, for reachable towers, what do we do? If the current quality factor is greater than max quality factor inculcated so far, update the max, update the coordinates. Else, if the quality factors are equal, Now we check them for lexicographic increment or decrement. Okay, so what was the last x coordinate? It is stored in answer at 1. So if it is greater than the current x coordinate, then our current coordinate is lexicographically smaller. So update our answer as x comma y. If the previous x coordinate is equal and the current previous y coordinate is greater, then also we are winning lexicographically. All right. So update our answer as x comma y. At the end, how do we know that no tower was reachable? If the x coordinate of all reachable towers is equal to int underscore max, this means that no tower was reached by us. All right. So for that case, update answer as minus 1 comma minus 1 and then return the answer. This was it for the very first problem. Now let's move to the second problem, which is minimum operations to reach target. The next problem is minimum operations to reach target array. You are given two integer arrays, nums and target, each of length n, where nums I is the current value at index I and target I is the desired value at index I. You may perform the following operation any number of times, including 0. Choose an integer value x. Find all maximal contiguous segments where index I equals to x. Okay, the value at index I equals to x. A segment is maximal if it cannot be extended to left or right while keeping all the values equal to x. For each such segment, L to R, update simultaneously num set L is equal to target L at L, num set L plus 1 is equal to target at L plus 1, and so on, which means that we update all the uh, values in that range to its corresponding target. Notice that target is equal to the target at that particular index. Okay, so uh, every one of them will be resolved after one operation. Return the minimum number of operations required to make nums equal to target. So let's solve the test cases to understand the problem statement well. The very first test case is nums I equals to 123, target equals to 213. Okay. Now what do the problem statement say? Is it says that we can choose a x and find all the ranges where every element in that range is equal to x. So what do it mean? Okay, let's copy this statement. Okay, this statement is very much equivalent to find all occurrence of nums, occurrence of x. Okay, how? Because it says that for all ranges that have values only equal to x, it does not restrict on us on the size of range. Okay, the size can be equal to a single element. All right, it means that if this range equals to x, that is all the elements in it equal to x, and this range also equal to x, all the elements in this range are also x, then we pick up all these ranges or all these indices inside these ranges. Okay, so with this, have we left any occurrence of x? No, because obviously if uh, it has no neighbor which is equal to x, then also one sized range will be selected. Oh, okay. So no, this means that we have selected all the occurrences of x. All right, and updated those values with their corresponding targets. So let's implement it. or let's solve the test case with what observation we have so far. We can, what do we want? We want to make this 1 equal to this 2, this 2 equal to this 1, and this 3 and this 3 are very much same. Oh, okay, they are equal. So no need to apply operation on this 3. Now choose 1. What are the indices that have num set I equal to 1? It is only the first index. Now convert it to its corresponding target. Now this is converted to 2. Okay. Similarly, now choose x is equal to 2. Now what are the indices selected? Okay. Now what are the indices selected? It is the first index and the second index. Even though our already chosen index is selected again. But our operation restricts us to a scenario that it will again be matched to its corresponding target. Okay, there will not be any harm in choosing an index anytime because it is always changed to its corresponding target. If they were already equal, then they will remain equal. All right. If they are not equal, then it will be num set I will be equal to target at I. Now num set 1 equals to 2. Really sorry. Now num set 2 equals to 1. So our array changes as follows. Now our nums and target are equal. So how many operations have we applied? We have applied 2 operations. So output is 2. Now for the second test case. Second test case is 414. What are the matching indices? Non-matching indices. This 4 does not match this 5. This 1 match this 1. This 4 match this 4. So we just need to replace this 4 with this 5. So choose x is equal to 4. What are the indices chosen? It is the first index which leads us to the observation or conclusion that num set 1 equals to 5. Now over to the third test case. This 7 does not equal to this 5. This 3 does not equal to this 5. And this 7 does not equal to this 9. So choose the first x as 7. Now what are the indices chosen? Indices are 1 and 3. So what will be the new nums? It will be 5 here and 9 here because the corresponding index is replaced with its target index or value at target. Now num set 1 equals to 5 and num set 3 equals to 9. Now choose x as 3 because no other option to convert this 3 to this 5. We need to choose x is equal to 3. Now what are the indices where num set I equals to 3? It is the second index. So how will it be changed? It will change as num set 2 equals to 5 now. All right. So what do we learn from this? For each unique value in nums, if it does not match its target, one operation needs to be applied. So what is our final intention? We need to find the number of unique values in nums, find the number of unique values in nums where at some, let's say that unique value is equal to x, where at some index nums at I equals to x and target at I is not equal to x. Alright. Can we say that this is our problem statement now? Why? Because for all such x, we can pick them and collectively convert to their target as we have observed. Alright. Now, what is the data structure we generally use to count the number of unique values? It is map. We can use an ordered map, or set, anything which we want. Okay, here we will use map, and our intention is very much clear. Just we need to write down this particular thing in the form of a code. All right. So what we will do, we will create a map to count the frequency or okay, the number of unique values. Now iterate over the whole array we are given. Now, if the current index is not equal to the current target, then let's say that this particular value nums I need to have an operation corresponding to it. So say that uh, there is one occurrence of this value in our requirement. Okay, at the end, how many values are there that have a operations requirement? It is equal to the amount of unique values in our map, which is given by the size of our map at the end, and just return this particular value. This is it for the second problem. Now let's move to the third problem. Okay, let's do the time complexity analysis of this particular code. Since we are using a map, which is an ordered map and not an unordered map, and we are iterating over whole array and updating the values in our map. So our overall time complexity will be equal to n log n. Could have we saved some of the computations? Yes, we could have used unordered map here. So that particular solution with an ordered map would be equal to time complexity of n. All right. And what is the space complexity? We are storing the values in a map which can go up till size n. That is the size of this nums array if all the elements are unique. Okay. So the space complexity again is O of n. All right. So this is it for this problem. Let's move to the next problem. So the next problem is number of alternating XOR partitions. You are given an integer array nums and two distinct integers, target 1 and target 2. A partition of nums splits it into one or more contiguous, non-empty blocks that cover the entire array without overlap. A partition is valid if the bitwise XOR of elements in its block alternate between target 1 and target 2, starting with target 1. Formally, for blocks B1, B2 up till let's say we have n blocks, so Pn, the XOR of first block is equal to target 1, XOR of second block equals to target 2, XOR of third block equals to target 1 again, and so on. It is alternating. Okay, 1, 2, 1, 2, so on. Return the number of valid partitions of nums modulo 1e9 plus 7. Note a single block is valid if its XOR equals target 1. It means that if the whole array is one block in itself and its value is equal to target 1. Why? Because we always start from target 1. So if such is the scenario, then also it is a valid scenario. All right. So what do the question mean? Uh, the question say that we are given a array. We need to partition the array into some blocks such that XOR of each block alternates between target 1 and target 2, starting from target 1. All right. So let's understand some of the properties of XOR, which we will use in solving this particular question. The very first property is the XOR of a number. Okay, this is the symbol of XOR, generally used in CPP. So we will use the same notation, same operator. A XOR of a number with itself gives 0. This is one of the property. What is the second property? Second property is X XOR Y equals to Z. If we are given this, then we can say that X is equal to Y XOR Z. Okay, we are given X XOR Y equals to Z. Then we can say X is equal to Y XOR Z. How? Let's prove this. We had X XOR Y. Let's XOR both of the sides, left hand side and right hand side, with Y again. Okay. Then we will get this. Now, in XOR, the order of operation do not matter. If we XOR 1 with 2 and then with 3, it is same as XOR 3 with 1 and then with 2. Okay, order do not matter. So if we XOR Y with Y, with the observation that or knowledge that order do not matter, we can do it in starting itself. Okay, and Y XOR Y is equal to 0 according to the first property. So the left hand side is equal to X now, and right hand side is equal to Z or Y. Z or Y. Okay, we already said that order do not matter. So Y or Z is equal to Z or Y, which is our final conclusion. Okay, just remember these two things. The first thing is X or X is equal to 0, and the second thing is if we are given X or Y is equal to Z, then we can write it as X is equal to Y or Z. All right. So let's move to the problem now. The problem was very much clear. So let's let's try to do some brute force work here. All right. Let's try to create a DP. Okay, DP at index I, let's say DP0 and DP1 at index I. What do we mean by DP0 and DP1? Number of ways to create a partition or valid partition such that it ends at index I and the last partition had XOR equal to target 1. Let's say this is DP1 and DP2. The DP2 means the same thing, just with a change that the last partition has XOR equal to target 2. Right. Uh, why do we have a DP idea here? Because Because for if we can create such a state, okay, if we can create such a state, then at the end, what, how can we answer our required answer? How can we find our required answer with these DP states? We actually want the number of valid subarrays ending at index n, that is over all the whole array. Okay, over our whole array, we want all the partitions ending at index n, whether the last partition be ending with target 1 or target 2. Okay, if it is not clear now, just stay with me. Let's have a dry run of this TP state. All right, then it will be much more clear. For example, in this test case, we had nums is equal to 2, 3, 1, 5. For now, just mug up this TP state. We will understand how we reached to this TP state later on and how we will compute the answer using this TP state. We will all discuss all of it soon. All right. Just let's try to fill the DP array. We have DP1 and DP2. So we want our, this is our first index, this is our second index, this is our third index, and this is our fourth index. All right. This is it. And what do we want? We want our partitions to start with target 1. And what is our DP state? DP state says that DP1 say the last partition we had was ending with target 1. Okay. So the how should the next partition start from? If the last was ending at target 1, the next should start with target 2. All right. The next should aim for target 2 because we are alternating over. The first partition is target 1. The second partition has XOR target 2. The third partition has target 1 again, and so on. So we will try to alternate between the targets as XOR. So for the first partition to have XOR equal to target 1, we say that initially the 0th or empty partition, empty subarray or empty prefix has uh, is a prefix ending with target 2. Just because if we alternate after this, or we create the first partition, it has XOR equal to target 1. All right, because we are alternating over every time. Now, what do the DP at DP1 at index 1 represent? DP1 at index 1 represents how many prefixes are there such that we can partition them alternately, and the last partition had target is equal to target 1. I think it must be clear now. Okay, can read this again. This is what I stated just now. Now, how many prefixes are there? Only one prefix exists for index 1. It is equal to 2. And what is the XOR of this particular subarray? It is equal to 2 again. Do it match target 1 or target 2? No, it do not match any of them. So how many number of ways are there? It is equal to 0. For DP2 at 1, it represents the prefix ending at index 1 such that the last partition has target equals to target 2, which is equal to 5. How many subarrays can we make for it to be valid as the last partition? Only one element is there, so only one subarray, which includes only one. So how many number of ways are there for DP, it is equal to 0 again, because XOR is equal to 1 and target 2 is equal to 5. Now DP1 at 2. Uh, how many subarrays are there? The first subarray is 2 itself. We are considering the prefix. Okay. The first subarray is 2 itself and the second subarray is 1. What is the XOR of first subarray? It is equal to 2. So is it equal to target 1? No, it is not equal to target 1. Now, what is the second subarray? It is 2, comma 1. What is the XOR of these two? It is equal to 3. Do it equal to target 1? No. So this is equal to 0. What are the XORs that we had? It is equal to 2 and 3. Do it match with target 2? No, it do not. So fill the DP value as 0 again. Now DP1 at index 3. How many subarrays are there? It is equal to 3. First subarray is 1. Second subarray is 1, 2. Okay, 1, 3. Third subarray is 2, 1, 3. Okay, ending at index 3. For the first subarray, which is 1, do it match with target 1? Yes, it matches with target 1. So, what do we want? We want the number of ways such that, okay, this 1 as a partition gives us target 1. So, the prefix before this one should end with target 2. Okay, the last partition at index 2 should be equal to target 2, which is represented by dp2 if we read it clearly again. Okay, what is our desire? Desire for dp1 at index 3. Since XOR of subarray 3 to 3 equals to target 1, we want how many number of ways are there so that subarray 1 to 2 can be divided into alternate partitions such that the last partition is equal to target 2. Alright. So, and this same thing is equal to dp2 of 2. Okay. dp2 of 2 represents number of prefixes or subarray 1 to 2. Prefix up till 2 is same as subarray 1 to 2, from 1 to 2. Okay. And how many number of ways are there to partition, which is same as what we intended in dp2, such that the last partition is equal to target 2, which is what we said here. Last partition has XOR equal to target 2. Alright, so to calculate dp1, we use dp2. Here, index 3, this particular subarray has value equal to target 1. So, what is the requirement now? What is the value of dp2 at index 2, which is equal to 0? So, here we write 0. Now, what is the second subarray? It is 3, 1. What is the XOR? It is equal to 2. Is it equal to target 1 or target 2? No, it is not. Now, the third subarray, it is equal to 0. 3 XOR 2, it is equal to 1. 1 XOR 1, it is equal to 0. Do it match with target 1 or target 2? No, it do not. Similarly, what are the values that we had? We had 1, 2 and 0. Do it match to target 2? No, it do not. So, answer is 0. Now, for dp1 at index 4, what are the possible subarrays or last partitions? It is equal to 4. Do it match with target 1? No, it do not. Then 4, 1. What is the XOR? It is equal to 5. Do it match with target 2? It matches with target 2 and not target 1. So we are currently considering target 1. Okay. Now third subarray, it is equal to 5 XOR 3. 5 XOR 1 is equal to 4. 4 XOR 2 is equal to 6. Do it match with target 1? No. Now the last one, 6 XOR 2, it is equal to 4. Do it match target 1 or target 2? No, it does not. So the value is 0 here. Now dp2 at 4, it is equal to, we already noticed that this particular subarray, okay, okay, we missed one thing here. Here, the subarray 1 comma 2, it was 3 XOR 2, which is equal to 1, and it matched target 1. All right. So how did we compute dp1 at 2? It is equal to dp2 at 0. Why? Because the subarray from 1 to 2 matches target 1. The XOR of subarray from 1 to 2 indices matches target 1. So the dp2 adds upon with dp2 of dp1 at 2 adds upon with dp2 of 0. All right. So this value will be added here. What do this value mean? How many subarrays are there? So that it ends with partition having XOR equal to target 2, or the next partition should be equal to uh, XOR partition XOR having value equal to target 1. All right. So there is one way for that particular thing, that is this particular partition. So dp1 at 2 represents 1. That is, there is one way to partition subarray 1 to 2 with XOR equals to target 1. It must be very much clear up till this part. Okay. If it is not, just repeat the statement with me and try to fill the values. All right. Now calculating dp2 at index 4. dp2 at index 4, how many subarrays are there? The first subarray value equal to 4, it does not match its target 2. The second subarray 4 comma 1, what is the XOR? XOR is equal to 5, as we noticed earlier. Now since it matches target 2, how will our dp2 at 4 will be updated? It will updated with dp1 at index 1 smaller than the starting index of partition. Okay, so this index, which is equal to 2. What is dp1 at 2? It is equal to 1. So it will be updated as 1 here. So at the end, we have 0 and 1 here. Okay, so how many valid partitions are there? It is equal to prefix 1 to n, or whole subarray, and the sum of dp1 and dp2. The last partition can be ending with target 1, or it can be ending with target 2. So it is represented by dp1 at n plus dp2 at n. So similarly, let's try to solve other test cases as well. For this test case, we have values 1, 0, 0. Let's create dp1. Initially, dp1 at 0 equals to 0, and dp2 at 0 equals to 1. All right, we discussed it earlier. Why? Now, what are the indices? Indices are 1, 2, and 3. All right. So for the first subarray, it is equal to 1, and it is equal to target 1. Okay. So how many number of ways are there to fill dp1 at 1? It is equal to dp2 at 0. All right. Because this subarray ends at 1, index 1. Okay. So fill it with 1. Now For target 2, do the subarray match with target 2? It is equal to 0 and the XOR is equal to 1. So it do not match. So fill 0 here. Similarly, at this position, uh, how many subarrays are there? Two subarrays are there. One subarray is 0 and second subarray is 0, 1. What are the XORs? The first subarray gives XOR equal to 0, which is equal to target 2. The second subarray gives XOR equal to 1, which is equal to target 1. So DP1 at 2 will be updated with index before this subarray, which is equal to index 0. So it will be updated with 1, and this position will be updated with DP1 at index 1, because this particular subarray matches target 2. Okay, so this particular prefix should end with target 1. So we refer it as DP1 at index 1. So it will be updated with 1, and this particular index, how many subarrays do it have? The first subarray is 0, XOR 0, second subarray 0, XOR 0, third subarray 0, 0, 1, XOR equal to 1. Okay, so how will DP1 be updated? It will be updated only because of this subarray with this value. Alright. And how DP2 will be updated? It will be updated because of this subarray and this subarray with values 1 and 1. Alright. This subarray corresponds to this value and this subarray corresponds to this value, is equal to 2. And at the end, what do we return? The sum of values at DP1 at n and DP1 at DP2 at n, which is equal to 2 plus 3, which is equal to 2 plus 1, which is equal to 3. Okay, we return 3. Now, what is the time complexity of our current logic? For each index, we count all the subarrays. Alright. For index I, we count how many subarrays are there before our current index, which have XOR equal to target 1 or target 2. What we are doing? For each index, find the number of corresponding indices which gives subarrays with XOR equal to target 1 or target 2. Or if we find the index as j, then we can say XOR from j to I equals to target 1. So we want to find all such j's for a given I such that the XOR of subarray from j to I equals to target 1. So what is the overall complexity to calculate this? It is equal to n into n, because we are iterating over all i's and then over all j's which are smaller than I. Alright. How can we reduce our time complexity? We can write our recurrence relation as dpi dp1 at I equals to all sum of dp1 dp2 of j for all j such that XOR from j plus 1 to I equals to target 1. Okay, this is what we were doing up till now. Now, we can also write this particular thing as prefix XOR up till j minus 1 XOR with target 1 equals to prefix XOR up till index I. Okay, now we want to find all such j's which satisfies this particular condition. What is the condition? Prefix XOR up till index j minus 1 XOR with target 1 equals to prefix XOR at I. Alright, okay, because in prefix XOR till j minus 1 we have XOR of index 1, index 2, index 3 and j minus 1, and then j, j plus 1 up till I. Okay, this is the left hand side. And what is the right hand side? It is 1, 2 up till I. Okay, it does not care about uh, these between things. It only ends at index I. And these two things are very much same. All right. Okay, now let's try to manipulate the above statement. We wrote the above statement from this particular condition that we are writing same thing in the left hand side and right hand side, but referring to the two things differently. Okay, now use the very first property that we learned. If we have x XOR y equals to z, then we can say x is equal to y XOR z. Okay, so prefix XOR of j minus 1 equals to prefix XOR of I XOR with target 1. All right. Now, what can we say? How have we manipulated our problem statement? Find all j such that prefix XOR of j equals to prefix XOR of I XOR with target 1. Okay. So, if we represent all our DP1s as prefix XOR j, okay, then for an index I, we just need to find out prefix XOR at I XORed with target 1. All the values that satisfies this particular condition. Okay, whose prefix XOR is equal to prefix XOR at I XORed with target 1. They all can be fetched in O of 1. Okay, for each index I, the corresponding previous j's, not the corresponding previous j's, the contribution due to previous j's can be calculated in O of 1. So what will our overall time complexity be? It will be equal to O of n. Okay, what was our intention? Our intention was just to find one matching properties which could reduce our recurrence relation from an O of n computation to O of 1 computation. So how did we manipulate our DP states? We manipulated our DP states as DP at a particular value XOR, let's say X says number of, okay, number of partitions, number of ways to partition a prefix. Let's say we have computed up till index I. So partition up till prefix I, let's say dp0 at x, such that prefix sum of that prefix sum up till I equals to x, and the last uh, partition was a last partition had XOR equal to target 1. This is represented by dp1. And what do dp2 represent? The same thing with target 2. Alright, this is it. Let's move to the implementation part now. How can we implement this? Very much same as how we computed the answer up till now. So let's see the implementation. So at first we create two map, okay, dp1 and dp2, which are referred as prefix ending with target 1 and prefix ending with target 2, because they store prefix XORs, so they are represented as prefix t1 and prefix t2. What did we initially assume? We assumed that an empty subarray or empty partition is a partition ending with target 2, so that the next partition or the very first partition starts with target 1, because they are alternating. All right. Now we want a modulo with m, so take that value as capital M. Now we want prefix XORs. Represent it as current XOR and keep taking the XORs with all the numbers. Now uh, the current XOR up till index I is represented by current XOR. Okay. Now how many number of ways are there so that there is a partition ending at current index and the last partition was having XOR equal to target 1. It is equal to prefix XOR of what is the current XOR? XOR with target 1. Okay, this is what we discussed earlier. For calculating dp1 at I, we wanted sum of dp2 over all j such that XOR of I plus 1, j plus 1 till I equals to target 1, which was later on calculated as prefix XOR up till current index XORed with target uh, 1. All right. So prefix XOR ending at T2, that is dp2, what we were using earlier. Okay. It is represented as prefix at T2. Now current XOR, the same thing. Prefix XOR up till index I. Current XOR is the prefix XORed with target 1. Similarly, for calculating uh, number of partitions current ending at current index, and they have XOR equal to target 2, it is equal to prefix XOR prefix XOR ending with T1 of current XOR with target 2. This represents subarray ending at current index with last partition as target 1 and target 2 respectively. Now add these new values into our prefix XORs, because our prefix XOR array do not take care of index. It just says that there is a partition up till this index, up till the current index, such that it has the last partition as T2 and uh, the index of last partition used, or the prefix sum of the last partition up till the last partition used, is equal to current XOR. Okay. Now at the end, we want the number of index ending at or number of partition ending at index n. So this was calculated here. Calculate the same thing. Okay. And return the sum of these two. Alright. And this gives us our answer. Although it was little complicated, but This is the best and most basic way to understand this problem. You can go through the solution once again. If you do not understand it, try to dry run. Try to dry run with the current prefix XOR scenario as well. Uh, Try to understand this mathematics properly, and eventually you will understand the solution. Okay, so let's move to the next problem after calculating the time complexity. What is the time complexity? We are iterating over the whole subarray or whole array and updating our prefix source. So this operation is a O of one operation. This operation is a O of one operation. This operation, because we are updating in a map, I guess we are updating in a map and we are not using an ordered map. So it is a log n operation. Similarly, this is a log n operation. At the end, this is also a O of log n operation. And overall, for whole subarray, we are doing log n operations. So n times log n operations. All right. What is the space complexity? How many unique prefix XORs can be uh, developed with this construction? At max O of n. Okay. Each index gives a unique prefix XOR. Okay. So the maximum number of unique elements that can be inculcated is equal to n. So the space complexity is O of n. So that is it for this problem. Let's move to the next problem now, which is minimum edge toggles on a tree. Okay, the problem statement say that you are given a directed tree with n nodes numbered from 0 to n minus 1. It is represented by a 2D integer array edges of length n minus 1, where edge at I equals to ai comma bi indicate that there is an edge between nodes ai and bi in the tree. You are also given two binary strings start and target of length n. For each node x, start x is its initial color and target x is its desired color. In one operation, you may pick an edge with index I and toggle both of its endpoints. That is, if edge is u comma v, then the colors of nodes u and v each flip from 0 to 1 or from 1 to 0. Return the array of edge indices whose operation transform start into target among all valid sequences with minimum possible length. Return the edge indices increasing order. If it is impossible to transform start into target, return an array consisting of a single element equal to minus 1. Okay, what do the problem statements say? The problem statement basically, in simple statements, say that we are given a tree. The values of or the colors of each node in the tree are represented by start, what are the initial colors, and what are the colors that we want is represented by target. Color of node 0 is 0 initially, color of node 1 is 1 initially, color of node 2 is 0 initially. 0 is red and 1 is green. Okay, what is our aim? To convert the first node to green color, second node to red color, and third node to red color, or zeroth, first and second, whatever indexing you want to use. All right. Now it wants us a sequence of number of edges. Okay, what is the operation provided to us? In one operation, we can select the edge. Let's say we selected this particular edge, the 0th edge. Okay, and we can toggle the color of both the neighbors of this edge. This edge has 0th node as its neighbor and one node, first node as its neighbor. So toggle both of these. Toggle both of their colors. So 0th node becomes green, first node becomes red. So what is the new color? It is equal to 100. Okay. and it is equal to the target color. So what do we output? We output the number or index of edge used. We use the first edge, that is 0, 1 edge. So we output 0. Alright, let's see the second test case. Let's say we have this particular scenario and we want 0, 0, which is correct, then 1, which is correct again, then 0, which is wrong, then again 0, correct, then again 0, correct, then a 1, which is wrong. Okay. This one, this 3, this particular 3 and this particular 6 needs to change their colors. Let's start thinking. What is the most restrictive one? 3 has two options. It can either change its color from by using this 4 or using this 5. But this 6 is more restrictive. It can change its color only using this particular edge, 5, fifth edge. Alright. So let's use this edge. Uh, Now, if we use this particular edge to, okay, let's copy this particular image. Okay. Now, if we use this particular edge, then this node is green and this node is green. All right. Now, can we use this edge? If we use this edge, then this becomes red. What is our aim first of all? We need to convert the third node, I guess. 0 was matching, first was matching, second was matching, third was not matching. Okay. And the sixth was not matching. Sixth we have updated. We want to update 3 as red. Now, if we use this particular edge, 0 becomes green. Okay. Which leaves 0 with no other option. Okay. So 0, this particular edge cannot be used because it is taking us away from our target. So, and another option that we have is equal to this edge. If we use this edge, this becomes red again. Now again, we are moving away from our target. Similarly, we are again moving from our target. Okay, because this is changing, but uh, it has other options. Okay, this particular subtree are the available options this particular node has, while this one and this one or this particular subtree has already been accessed enough. All right, now we want to change its color to red again. Apply operation, change this to red and this to red again. Now this subtree is handled properly. This is converted to green and this is remained as red as we wanted earlier. Okay. Now this is red and it wanted to be blue, and this is blue and it sorry, this is red. This is red and it wanted to be green, and this is green and it wanted to be red. Okay, so this is a really good scenario. Let's apply our operation. Okay, I'm really sorry, but this wanted to convert back to green and this wants to convert to red. If we apply our operation on this particular edge, both of them will be toggled and our requirement will be satisfied. Okay, so this is converted to green, converted back to green, and this is converted to red as we wanted. Alright, and our requirement is satisfied. What are the observations we had using this particular example? Try to fill or convert the restricted nodes first. Okay, how many number of restricted nodes are there? I can say each leaf is a restricted node. How? If a leaf's value do not match the required value, then it has only one option, its parent. Or because it is a leaf, it has only one neighbor. All right. Taking any particular node as a root, then its parent is the only neighbor it has. So if its value do not match, we would want to apply an operation and change the value of its parent as well. After this, we cannot use this node. After removing these leaves, some new nodes, let's say we remove all the edges from leaves, that is, we remove this particular edge, we remove this particular edge, remove this particular edge, and we remove this particular edge from this tree, let's say. Okay, then we are left with this part or this subtree. Then this is a leaf. This is a leaf. Okay, some new leaves occur every time. And they are the restricted ones now. At the end, using this operation only, we uh, compute or evaluate the whole tree. Okay, if the last remaining node still needs some edge to change its value, answer is not possible. Okay, how? Because every time we are removing a node, we are sure that its value cannot change any further. If we try to change its value, then we are moving away from the target. Okay, that is, we need to do the same operation once again. Okay, because this leaf had only one option. All right, this particular edge. If we uh, if it matches the target value and we change its color, then we would want its value to change again. Then again we are using this particular edge only. So overall improvement is nothing. That is, we applied a operation to change toggle these two's color, and then we applied a operation again to toggle these two's color. So overall impact is null. No impact has been done. Okay. So all the leaves need to be uh, evaluated only once, and then if they are removed, they cannot be used any further. Okay. So by using this operation, we are eliminating some of the nodes which are currently the root nodes. All right. Currently the leaf nodes, and a tree always has a leaf node. All right. And if we are removing some of the leaves from a tree, it will always remain a tree. It is a property. So it will have leaves again. So using this operation, we can always manipulate or eliminate some of the nodes. And at the end, we are left with a single node. Now, if this node has the same source and target value, we can clearly say that apply a operation. We need not apply a operation, and all these operations which we have applied so far is a valid operation. If its value do not match the target, no particular another construction can be done so that the left node matches the color of target. All right. So what do we need to do? We just need to implement this. What are the ways to implement it? We need to uh, travel to the leaves first. Okay, we can do the same thing using, we can do this thing using BFS as well as TFS. How using BFS? Let's say this was the tree. First insert all the leaf nodes, insert both of them. Now remove them from the tree. Now again insert the leaf nodes, because the new leaf nodes will always be a neighbor of removed nodes. So we can do this in O of E. E is the number of edges. Iterate to this edge and insert the new leaf node. Iterate to this edge, insert the new leaf node. Iterate to this edge, insert the new leaf node, and so on. Or we can do this using DFS. So we will be doing this using DFS itself because it is easier to implement, obviously. Uh, in DFS, we go to the depth and we want to evaluate the leaves first. So first go to the leaf node. Okay. Now, if this leaf node matches the source and target value, no operation need to be applied. If it do not, apply a operation here. And due to this, one operation will be applied to its parent as well. All right. Similarly, move to its second child now. If a operation needs to be applied here, it needs to be applied in its parent as well. All right. Because two operations have been applied here, it is equivalent to applying no operation. And if its value do not match, uh, can we do operation with its children? No, its children have already been removed. So we need to apply operation with its parent. Okay, if it does not match its value. So it is colored as red. Red means that one extra operation is applied due to the evaluated child. It does not meet the same red and green which we discussed earlier. And in the similar manner, go to its leaf, check if operation need to be applied. If it needs to be applied, change the color of parent. Similarly, in the second leaf, if operation needs to be applied, color the change the color of its parent, else do not change. Now if the color of this new leaf after removing these two leaves matches, then no new operation needs to be applied. If it does not match, one operation needs to be applied here. So one operation will be applied on this node as well as the root node. All right, so this is the DFS logic that we have. Let's move to the implementation part now. uh, So we have our graph or tree in the form of edges. Let's convert it in the form of a adjacency list. We also want the indices of edges that we are using. All right, so let's create a map to map a particular edge to its index. Because we want uniqueness in each edge, so represent a edge with the number of nodes such that a pair represents a edge and the pair has values of the connecting nodes, and the first part of pair has the minimum value and the later part has the maximum value among these two nodes. All right. here is more visual representation of this thing that I said. Now create a adjacency list using this part. Now map contains the corresponding indices. Now create a vector of chosen edges. Whenever we will be choosing a edge, we will be choosing that node and its parents node. So insert that particular thing inside the chosen edges. Now run a DFS. What do DFS do? DFS returns if the subtree starting from the current nodes needs a extra operation from its parent in order to be satisfied at the end. If it does, then it returns 1, else it returns 0. Now at the end, if the last node or the root nodes require one extra operation, just return -1 because our tree cannot be satisfied from source to target. Now let's move to the DFS part. Now cur represents the current color and required REQ or required represents the target color. Let's say sum is equal to 0. Sum represents how many of its children needs an operation to be applied, extra operation to be applied, which involves the current node as well. Moves to its neighbor. If the neighbor is not parent, run a DFS. DFS will again return 1 or 0. 1 means that that subtree requires one operation. 0 means that that subtree requires no operation. Now, if cur plus sum modulo 2, because color is alternating, red then green then red then green. If sum is 1, then red will be converted to green. If sum is 2, then red will be converted to green and then will be converted to red again. So it is modulo 2. If this particular thing is equal to required, then no extra operation needs to be performed with its parent. All right. Else one operation needs to be performed with its parent. So chosen edges dot pushback node comma its parent, and for this case return 1. Now create answer. Answer has the corresponding indices of edges uh, with respect to the chosen edges in the format that we have decided. Minimum value and then maximum value inside a pair. Inside answer, push back the index we get corresponding to the current chosen edge, and at the end, because we want the returned indices in increasing order, so sort this particular answer and then return it. That is it. Let's discuss the time and space complexity. Because we are running a DFS, it is number of nodes plus number of edges. Number of edges is n minus 1, which is approximately equal to O of n. Alright, what is the space complexity? Okay, we are also having a map for each edge. So there are n minus 1 edges. So n log n. Alright, now space complexity. We are choosing the edges, uh, which can go up till the number of edges we have, which is O of n, and answer is also an O of n thing. Similarly, this adjacency list is again a O of n thing, and chosen edges is again a O of n thing. Map is also again a O of n thing because it is having all the edges corresponding to it. So this is it. It's well passing under the given constraints. So thanks for joining. We will meet again very soon. All the best for the upcoming contest. We will be updating the Code Forces contest of today as well. Stay tuned. Thank you for joining.